Continuing on with multiple regression, we're going to talk a little bit about more of the generalization and how to actually run the test. So the generalization, we really want to be able to take this model that we create that is based upon our sample, and we want to be able to generalize that to our entire population. So the issue that we have with this is we're going to have to collect adequate data in order to be able to do that. But there's several assumptions that have to be made for the generalization, and obviously violating these assumptions does not allow any generalization. Which means we cannot draw any conclusions about our target population. In order to test generalization, we just need to simply cross-validate the model. We're going to talk a little bit about how we do that when we get to the analysis part as well. So for a sample size, how big of a data set do we have to be able to test the model, to be able to test the predictors? Essentially, we want very basic 10 to 15 cases per predictor. So if you're using 5 predictors, you're going to have to collect information from 50 to 75 different cases. However, the size of your sample really impacts the effect size as well as the power of your test. So let's think about this slightly different. In order to test the model, the minimum number of cases we should have should be 50 plus 8 times the number of predictors. To be able to test the predictors themselves, you should have 104 plus the number of predictors. So if you go in that range and you choose the maximum, you should be able to say, yeah, the model is good, it's generalizable, and you can kind of move forward. We have some pretty straightforward assumptions that we have to meet for multiple regression. Obviously, the outcome must be continuous. Predictors could be continuous or dichotomous. They could be one of two things. And we have to make sure that we have a non-zero variance for our predictors. So none of our predictors can have a zero variance. Linearity, obviously the model will be very poor if you don't have a linear relationship, because this is a linear multiple regression. Depending upon if you want to do a quadratic or a cubic regression, if your data plots in that format, you can just do a simple multiple cubic relationship. But that really complicates the matter, and multiple regression is pretty complicated enough, so I just thought we're going to stick with linear for this course. We want to make sure that our predictors are not correlated with any external variables, which means any variable not included really should not impact our outcome. And then our data, as we discussed before, needs to be independent. Now we've got some assumptions that are a little bit trickier. We cannot have multicollinearity, which means our predictors cannot be highly correlated with each other. Homozygosity. For each value of the predictor, the variance should be constant, the variance of the error term. And those error terms should be uncorrelated, or we should have no independent errors. And we should have normally distributed errors, which means our residuals should have a normal distribution with a mean of 0. Alright, we're going to go over each one of these assumptions, how to check it, and what it really means. Alright, so if we meet all of these assumptions, we should have an unbiased model, which means that our sample is generally from the population. However, it is possible that that might not be true, depending upon the sample that you've collected data on. And unbiased simply decreases the likelihood that we don't have that problem. Alright, one of the things that we need to do for generalization is to cross-validate the model. So that's assessing the accuracy of the model across different samples. We can also look at our adjusted R-squared and data splitting. We're going to focus more on the adjusted R-squared. Which is going to indicate the loss of predictive power. And sometimes we call that shrinkage. So what does that R-squared tell us again? It tells us how much variability we have in the outcome variable that is accounted by the predictors in the regression model. Our adjusted R-squared says the exact same thing as R-squared, except you're going to replace the word sample with population. So the adjusted R-squared is how much variance in the outcome can be accounted for by the regression model from the population. So obviously, if we have a very, very small adjusted R-squared, we have very little variability. Here's a way to calculate adjusted R-squared. Good news, SPSS also does it for you. Now you can also randomly split the data. Again, we're just going to briefly talk about this because this is pretty tedious to do. And if you end up having an adjusted R-squared that is acceptable, then you really don't need to worry about even doing the data splitting. But once you split the data, you're actually going to compute your regression equation on both half sets of your data. And then you simply compare the results. If you're doing a stepwise regression, it's not going to be a 50-50 split. It's going to be an 80-20 split. And on the 80%, you're going to use stepwise, and on the 20%, you're going to force the model. And then you compare your R values and your coefficient values between the two samples. Multicollinearity, we already said, if the predictors are highly correlated, this is a problem. Now, if we have perfect multicollinearity, the between the predictors, the regression coefficients that we get for each one of those two predictors are interchangeable. So all multicollinearity says is you've got two predictors that are in the model that are telling you exactly the same thing. A really good way to avoid this is simply remove one of those predictors. So there's three problems that we have if we have multicollinearity. We have untrustworthy coefficients. So what happens as collinearity increases, our standard error of our b-values also increases. So that's not a good thing. Our regression coefficients are also unlikely to represent the population. And we end up with a really unstable model or regression equation. Now, what's also going to happen, we're going to limit the size of R. And why is that? We've got an overall variance that in the outcome that's accounted for by the two variables. At best, it's only a little more than just the one variable. Usually, it's the same. The R value does not change. So the importance of the predictor, we don't know. We won't be able to tell you what the importance of any predictor is when we have multicollinearity. So how do we test for it? Well, the first thing, you can go ahead and scan your correlation matrix. You should have a concern if that correlation matrix has any correlation coefficients greater than 0.8. You can also look at a variance inflation factor. And this is usually not done until after the analysis, the regression analysis is already done. So at least that correlation matrix, that is your first step. And if it's greater than 0.8, just choose one of them, not both. And that variance inflation factor is very similar to the correlation. It's telling you whether or not that one predictor has a strong linear relationship with another. Alright, so when do you have a problem? You should probably have a concern if those values are greater than 10. There's also an average variance inflation factor. If those average is greater than 1, it should also be a concern. Now you can take your tolerance, or 1 divided by the variance inflation factor, and you could say that you've got serious problems if you have values that are less than 0.1. And you can ramp that up to a serious concern if those values are below 0.2. Other ways that you can look for the multicollinearity, eigenvalues, condition indices, and variance proportions. We'll talk about some more of those when you get to multi-regression analysis and we actually have output that we can look at. Other assumptions, the homoscedasticity or independence of errors. You're simply going to want to plot your Z residual value versus your Z predicted value. Normality of errors. You're going to want to do your normality probability plot. And one last word of warning. Any statistical package that you use for analysis is going to be more than happy to generate some output. And that output could be based upon any garbage that you decide to feed into the data editor, right? And more importantly, the software is certainly not going to tell you if your model is valid. It can give you some generalizable values, it can give you some output, but if you've got a sample that is not representative of the population, but you have very low shrinkage, well, it still doesn't mean the model is valid, right? So any software will be happy to do anything that you ask it to do, but you do have to be the brains behind any of this multiple regression, and you do have to figure out and do some work to know what to put in the model, how to put it in the model, and when to put it in the model. And that's hopefully what you've got at least so far. Now let's go over a real simple example on how to do this in SPSS. So we've got a song, it's played on the radio, and obviously there's an attractiveness of the band. Since internet is so prevalent, we know what the band exactly looks like upon assembly of that band. So does the attractiveness or the number of times it's played, I should have said not necessarily on the radio, but maybe accessible on the internet, does that impact song sales as much as the advertising budget? Because we knew, right, now it says as much as previously determined advertising budget. Now we've got those words previously determined. What does that mean? So we're going to do multiple regression, and this is where I want you to watch the SPSS doing multiple regression example. I'm doing it in SPSS. You're going to create block 1. And in this block 1, we already know, right, that advertising budget sales that is going to impact sales. Advertising budget impacts sales. So advertising budget is going to be put into block 1, right? And there's only one piece of information going in here. So you're going to go ahead and use a forced entry. Block 2, we said we've got attractiveness, and number of plays. So we could use a different method, right, with block 2. Let's say we looked at some correlation and they're about equally correlated. So there's 2 ways you could enter this data. You could do stepwise, or you could force them both in. If they're both equally valuable, you can go ahead and force them in. And when we get to the analysis, that's what you're going to watch, is I'm going to force them in. Or you could go with stepwise, either the forward or the backward. Now, it's going to ask you for, you can go to regression statistics in your entry format. You have got to check for multicollinearity, and you have got to check for independence of errors. And that independence of errors is actually called the Durbin-Watson. Okay? So in regression statistics, yes, you're going to want estimates for the regression coefficient. You're going to want confidence intervals for your regression coefficients. You're going to want the model fit, the R-squared change, the descriptives, the part and partial correlations, the collinearity diagnostics, Durbin-Watson, and case-wise diagnostics for outliers outside 2 standard deviations. Now, in terms of regression statistics, the estimates, those are the estimate v-values with your test statistics. Your confidence intervals will be based upon the unstandardized regression coefficient, and your covariance matrix is going to give you your covariance, correlation coefficients, and the variances. The model fit will give you your R-squared, and adjusted R-squared, so you don't have to calculate the adjusted R-squared. It will give you the R-squared change, and that R-squared change is the change in the R-squared resulting from the inclusion of a new predictor. So here we've got 2 blocks. It's going to look at Model 1, which will have an advertising budget in it. Model 2 will have advertising budget, attractiveness of the band, and number of plays. That R-squared change is going to say how much better is Model 2 versus Model 1. Any descriptives that you ask for, such as the mean, standard deviation, and matrix, will be provided. You'll also get part and partial correlations. Your collinearity diagnostics will give you a ton of information. Durbin-Watson, again, that's your independence of errors. Your case-wise diagnostics will really give you all the information on your residual statistics. And then on your regression plots, you're going to have a lot of information, and you could go ahead and save this information as well. So on regression plots, you've got to choose which one of these pieces of information do you want to plot. You're going to want to plot z-pred and z-residual against each other, and that's going to determine whether or not our assumption of random errors and homoscedasticity have been met. So those are the 2 that you want to pull up on you do regression plots. The regression plots it will produce are scatter plots of all those residuals. You might be able to see the outliers, and you might be able to see if there's any type of nonlinear influence. Sometimes these regression plots are really useful in detecting some type of collinearity or multicollinearity. The regression plots can also give you your histograms, so you can check your normality of errors, and your normal probability plot, again for normality of errors. Now in terms of your regression diagnostics, all that box is going to do is tell you how well the model fits your sample. and it's going to be able to help us detect cases with large influence. So you're going to want all of your predicted values, your standardized residuals, your standardized DF fit, and all of your distances, the Cook's, Mahalanobis, leverage values. And that's pretty much it. Now when it saves all of this information, it shortens all of that data, and it will save it in your multiple regression file. And this is what the headings will be, and that is what they will mean if you save all of that information. And that way you can look at that when you get to the analysis part to figure out what is going on in your data. Alright, so the next thing that you're going to want to do is you're going to want to go to the multiple regression analysis and really try to understand all of the output. And I would like to apologize, the multiple regression analysis output is the most ridiculous you've seen to date. There's just a ton of output, and that is essentially associated with the fact that we have just a ton of assumptions that we have to check, and most of those output pages are associated with those assumptions, the outliers, and the influential cases.